should now be starting to think of the double integral in a more general context. I guess in a more abstract setting, relying on the definition as a limit of a double Riemann sum. Okay, now in that example, I just pointed out that, I didn't work through the details, but I pointed out at some stage to evaluate one of the integrals we had, you had to do a trig substitution to evaluate it. And I just made the point at the end of the example that perhaps we could use a different coordinate system, or perhaps we could have used a different coordinate system at the start of the calculation, so that when we applied Fubini's theorem to evaluate that double integral, we ended up with just constant bounds in both integrals, right? All four bounds of the integrals were constant, right? That would be, I guess you could say, an ideal coordinate system to use. All right, we've seen how to deal with more general regions by breaking it up into these building blocks, these type 1 and type 2 regions. And one of the things we saw is when we did that, and apply Fubini's theorem, the integral, or the inner integral, or the bounds always are, well, usually are functions, unless it's a rectangle, right? The bounds are usually functions of the other variable. All right, and so, sometimes this can be manageable, but other times it can be quite challenging. Now, one thing we would want to look at today is what happens if at the outset we change the coordinate system we're using and just think about the double integral, or rather, really the iterated integral, I should say. We think about it in terms of a completely different set of variables rather than the rectangular variables, x and y. Okay, now I'll refer to those variables as the rectangular coordinates or rectangular variables. How can we deal with introducing a new coordinate system that might be more naturally associated with the region of integration? Right? And when I say more naturally associated with, I mean that we use it in such a way so that when we apply Fubini's theorem, the bounds of those iterated integrals are all constant, right? This is what I mean by natural, right? It has some natural association with the region. Now, to demonstrate this point, what we're going to look at is one particular coordinate transformation known as polar coordinates. Some of you may have looked at polar coordinates before. You may have come across this coordinate system. But now we want to look at this in the context of double integrals. All right, so let me just start by telling you what the relationship is between rectangular coordinates and these polar coordinates, and indeed how we define these polar coordinates. All right, and so these are the coordinates to use if the region we're considering is circular or part of a circle or has something to do with circles. Okay, with a circular or annular region, right, like in the shape of a ring. Okay, so let's see the relationship. So say we've got a point in the plane with coordinates x and y. What I can do is draw a straight line from that point to the origin. Okay, and I can measure the length of that straight line, and this is one of the polar variables I'll call r. All right, so one feature of this particular polar variable, r, is that it's always greater than or equal to 0 because it represents a distance. Okay, so that's the distance that point lies from the origin. All right, so now I've got this line drawn in from the point to the origin, and if I measure the angle that that line makes with the positive x direction, I'll call that the variable theta. Okay, so one thing we can do now, just from this picture, look at what happens in the positive quadrant, use what we know about the cosine and sine functions to extend this to all of the plane. We can measure, just using the definitions of cos and sine, we can measure these distances. All right, so one thing I can see immediately, just using the definition of cos, is that this distance here will be r cos theta. All right, and and that distance there, at least for this quadrant, that distance is just the x coordinate. All right, but this extends to all of the plane by the definition of the cosine function. All right, similarly, we can measure that as r sine theta, right? Just using the fact that I've got a right-angled triangle there, using the definition. Okay, now one thing I can see, as I've said, we can define these functions cos and sine for any value of theta, but what's important in this case is extending it to all of the plane. All we need to consider are values of theta, or at least a range of values that go from 0 to 2 pi. So here in the diagram, I've labelled a few of the, I've labelled the x and y axes in the positive and negative directions, just to show you what values of theta they correspond to. So we start, theta equals 0 corresponds to the positive x direction. As theta increases, so this line sweeps out in an anti-clockwise direction. Okay, until we get to the positive y-axis corresponding to theta equals pi on 2, and so forth. All right, so increasing theta, we go up to pi, 3 pi on 2, and then at 2 pi, we're back to where we started. All right, but now just note that I've included some negative values here, negative pi on 2 and negative pi. Well, that's okay, and in fact, we can still use those values of theta, and I'll just give you an example of where we might need such values. So there's I guess it's a convention, and I mean, this goes back to just keeping things simple, that say we had some circular region or some part of a circle that was centered at the origin, and we're only interested in one half of it that corresponds to positive values of x. So if we only consider values of x which are greater than or equal to 0, then the convention is that we usually just take as our range of values for theta from negative pi on 2 to pi on 2. So for example, well, you think about the diagram in the xy plane. So if we were just interested in part of the circular region, just for that half of the plane that lies to the right of the y-axis, okay, then if we were to use this in a double integral, it's actually more convenient just to use one interval for theta rather than saying theta is from 3 pi on 2 to 2 pi, and so as one part of the region, and theta's from 0 to pi on 2, okay, which we could do, but it's just a convention. Rather than split it up into two separate regions, we just use one region, and we just I guess reshuffle our domain for theta. Okay, so that's just a convention. All right, so we end up the polar transformation, or that is the relationship between the rectangular coordinates and the polar coordinates, is just x equals r cos theta and y equals r sine theta. So what we really want to do is learn how to use that in evaluating double integrals over regions with some kind of circular symmetry. All right, so what we'll do is go right back to when we first considered the double integral and that problem of determining the volume below a surface and above a region in the xy plane. All right, so let's go back to the start. Let's keep things simple. So we say let's consider the volume of a solid beneath the surface with equation z equals f of x and y. So we've got some function of x and y, but now for simplicity, we'll just assume that this function only takes on positive values over the domain that we're interested in. All right? Just to keep things simple at the start. Okay, and above some circular region or part of a circular region in the xy plane. All right, so remember what we did previously when I introduced a similar problem, but using rectangular coordinates. We started off with a rectangle and we superimposed a rectangular grid over that region. Okay, and then made approximations where we chose a representative point inside each of those sub-rectangles. Remember I was calling the little grid squares sub-rectangles. Evaluated the function at the representative point. That was going to be the height of our box. Okay, we can work out the volume of a box, right, of just depth times width times height. The height is the value of the function at the representative point, and, well, times the base area gives the volume of the box. Okay, so we're going to use a similar idea, except now we're not going to be superimposing a rectangular grid. We're going to superimpose what you might call a polar grid over this circular region. So here I've got a diagram of just part of that circular region that's centered at the origin. Okay, so here's I guess I'll just call these polar grid squares, or polar rectangles. I'll just use that language for want of a better phrase. So what we'll do is use a similar approximation to first approximate the volume below the surface by approximating the volume below the surface and above one of these polar squares or these polar rectangles, right? And I'll use exactly the same approach, right? Choose a representative point, call it P, in one of these polar squares, evaluate the function at P. That's going to give me the height of the box. The only thing now is the box isn't going to be a rectangular box, right? It's going to look something like this. And once again, I apologise for my horrible three-dimensional diagrams. But look, the idea is this is just, I guess, an exaggerated version of that one of those polar grid squares. Okay, but the sort of object we're dealing with might look something like this on a good day. So we're choosing a representative point inside our grid square in the xy plane. We're evaluating the function at that point, and then that's going to give us the height of this box. But you can see the difference now is the cross-sectional shape is not a rectangle, right? So what we've got to do is try and work out, well, how can we give an expression for the volume of that box? All right, we can still use the formula base area times height. So what it comes down to in that case is working out what the base area is. Okay, so in this case, remember using polar coordinates, we've got the coordinates r and theta. So one thing in these grid squares, the r variable changes in this direction along these radial lines, okay, from the origin or from the centre of the circle. And in this direction, we have a change in the angle that I'll call delta theta. All right, now let's just say this point, this representative point in my grid square, let's just say that corresponds to a distance from the origin. I'll call r star. All right, so now what we can do is try and work out, or at least estimate, given these details, what the base area for that polar box, I don't know what to call that, polar cylinder, whatever you want to call that. It's part of a cylindrical shell, right? So again, here's an exaggerated diagram, an exaggerated diagram, or an exaggerated version of one of those grid squares. So we've got our representative point somewhere in the region. Okay, we've got the dimensions being delta r this way. And now what I'm going to do is approximate this as, so I'm going to make an approximation here. And what I'm going to do, let me just move this down. What I'd really like to do is grab hold of these two edges and straighten them out so they're parallel. Right? So I know the length of these edges will be delta r. But what I want to do is straighten them out so they're parallel. And this circular arc that passes through the representative point P, I can actually work out what that length is. And so what I could do for my sort of centered at my representative point, I could grab those two edges, straighten it out so the edges are parallel, and then approximate that base area as just the area of a rectangle. Okay? And what I really want to do is straighten out this line that's part of that circular arc. So, what is that length there? So I'm really talking about the length of that circular arc there. I can just take to be r star times delta theta. All right, it's just the formula for part of the arc of a circle. All right, I mean, you think about that. If I take part of a circle of radius r, right, and I want to know that length there, I want to know this length here, that's just going to be r times theta, right? I mean, think if you go the whole way around the circle, right? That's the circumference of the circle. That's 2 pi r, right? That's theta equals 2 pi. So if you take half the circumference, that's pi times r, right? So theta equals pi, and so on. So you take any angle theta, then that distance is going to be theta times r. So that's all I've written here, right? I've got the radius of this circle on which this point P lies is r star times the angle, and the change in angle is just delta theta. All right, so I'm stretching that out so it's like a rectangle. So I've straightened out this edge, so that's delta r in this direction, and here we've got r star times delta theta. All right, so now it's just a matter of now we can work out, just as an approximation at least, the volume of this box is just going to be the height, which is the value of the function at the representative point, times the base area. And the base area then is just going to be approximated as the dimensions of that rectangle that I've straightened out, right? This r star delta theta times delta r. All right, so that means the volume of one box, now we're using polar coordinates, and the transformation from rectangular coordinates, or the way it's related, is that if x star and y star are the coordinates of my representative point, then I can represent those as r star cos theta star and r star sine theta star, where those are the coordinates of the representative point in terms of the polar variables. Okay, so the volume of one box then is just the base area times the height. Okay, so that's exactly what that is. The base area of one of those cylindrical shell blocks, whatever you want to call it, polar blocks, the base area, and the value of the function at that representative point is just the height. Okay, but that's only one box. Right, we repeat this process for all our grid squares and sum up all the individual volumes. So we end up with an approximation to the volume below that surface as just the sum over the polar grid, right, the polar grid squares of this product of base area times height. Okay, which is just expressed all in terms of polar variables now. But now what we can do is take smaller and smaller grid squares, right? And get a better approximation in much the same way we did when we looked at rectangular coordinates. Okay, and in the limit, as delta r and delta theta simultaneously go to 0, our volume is just equal to that limit of this summation. All right, and that's what the double integral is. Again, but now we've got double integral in terms of these new coordinates. Okay, so I guess what we've got then is a way of expressing a double integral in terms of rectangular coordinates as a double integral in terms of polar coordinates. Now here, I'm not saying anything about Fubini's theorem, right? So even though I've used a slightly different notation, so it could be a little bit misleading, now I've used this notation rather than, up till now I've been using dA, right, for the infinitesimal element of area in my double integral. So now on the left-hand side, I'm using dx and dy just to indicate that, all right, the integral on the left-hand side is in terms of rectangular variables. The integral on the double integral on the right-hand side is in terms of polar variables. All right, so now I guess the important thing is we're changing from rectangular variables, so the dx, dy becomes the r d theta dr. Or here I've written r dr d theta, and just at this stage, ignore the order of the dr and the d theta, the dx, dy. So it's got nothing to do with order of integration, right? I'm just talking about the double integral, not the iterated integral. So I haven't applied Fubini's theorem or anything like that yet. Okay, so that's how we deal with double integrals in polar coordinates. So one feature is this term, this r appears, right? Because we're now using polar coordinates, right? This r appears. That's got a special name. So in the expression r d theta dr in terms of polar variables, that r is called the Jacobian of the transformation. All right, so that's the Jacobian corresponding to the polar variable transformation. It turns out if you have any variable transformation, or if you have an arbitrary variable transformation, there's going to correspond a Jacobian to that variable transformation. And the Jacobian always appears in this way when you transform from rectangular coordinates to that new coordinate system. In fact, in general, if you have, say, some new coordinate system u and v, and you write down these two coordinate transformations. So we've got these two functions of u and v, which tell us how u and v relate to x and y. Then the Jacobian, and I'm not going to prove this, but actually we will be able to prove this a bit later on in the course, in the vector calculus course, when we start looking at parametric surfaces. There's a very easy way of proving this formula that I'm about to give you for the Jacobian. Okay, but the Jacobian, in this case, works out to be, so given these two functions, these variable transformations, works out to be the determinant of a 2 by 2 matrix, where in the first row we have the partial derivatives with respect to u and v, and in the second row, the partial derivatives of x with respect to u and v, and then in the second row we have the partial derivatives with respect to y and v in that same order. All right, now you could actually go to the polar variable transformation, x equals r cos theta, y equals r sine theta, or if you like, x equals u cos v, y equals u sine v, plug it into that determinant formula for the Jacobian, and you'll find you end up with u. Okay, or in other words, you'll find you end up with the same Jacobian that we've found here using a geometric argument. Okay, anyway, this sort of thing will be relevant for assignment 2. Can't remember what question it is, maybe question 2. I've given a variable transformation in terms of variables s and t. Right, and so when you work out, I think at some stage I asked you to evaluate a double integral using those coordinates. So you'll have to work out the Jacobian of that transformation and then use it in this way. Okay. All right, so that's polar variables. That's how we use polar variables anyway. And so that's one particular variable transformation that we're focusing on in this course. So here's an example. Let's find the double integral of this function, e to the negative x squared plus y squared, over this region D, where D is just the region in the xy plane bounded by the circle of radius capital R. All right, now just one thing to note. Remember, I think it was earlier this week, was it Monday's lecture? I was talking about elementary functions and non-elementary integrals and so on. Just one thing, I'll just remind you that this is actually an example, e to the negative x squared. That's an example of an elementary function whose antiderivative is not expressible in terms of elementary functions. All right, so just an observation to start with. All right, so the region in the xy plane is a circle centred at the origin. So we know the equation is x squared plus y squared equals capital R squared. So we know it's a circle of radius capital R that's centred at the origin in the xy plane. So that's the region called D. All right, so it's at this stage we see it's a circle. The region of integration is as part of a circle or part of a disk, right? In fact, it's the entire disk. So we use polar coordinates. All right, so the transformation is x equals r cos theta, y equals r sin theta. There's got to be a mark in that for writing down a variable transformation on the final exam, if it's relevant to the question that's being asked. So now what have we got in the function? We've got an e to the negative x squared plus y squared. So what does x squared plus y squared look like in terms of polar variables? So that's r squared cos squared theta plus r squared sine squared theta. So you can see I've got a common factor of r squared, and that's just multiplying cos squared theta plus sine squared theta, which is an identity, or using an identity that equals 1. So this just simplifies to r squared. Okay, and I can also give an expression for the region in terms of these polar coordinates. So this D is now the set of all points with polar coordinates r and theta, such that r is between 0 and capital R. Remember, r equals 0 puts us at the centre of the circle. All right? Remember, this polar variable r is a distance. Okay, it's the distance from the origin in this case. So r equals 0 puts us at the origin, which in this case is the centre of the circle. R equals capital R. I should have used another variable name. Anyway, it doesn't matter. R equals capital R puts us on the edge. Right? So we're interested in all values, or in all points that lie a distance less than capital R from the origin, right? So if the polar variable R was greater than R, that would give us a points outside the region. We're not interested in those. Okay, as for theta, well, remember, so theta is, if we take a point inside the region, draw a line to the origin, theta is the angle that line makes with the positive x-axis. Right? So since we're interested in the entire circle, not just a slice of pie or something like that, we're interested in all values from 0 to 2 pi. All right? So here's the beauty of using polar variables, is the bounds of integration, all 4 bounds, are constant. This is what I mean when I say we've got a coordinate system that is naturally associated with a circle. All right, over the page. And I'll just make the point that also in the double integral, when we change variables, remember we replace the dx dy with r d theta dr. So importantly, we include the Jacobian. All right, so that implies then that the double integral, that, well, I'll write it out. What is it? E to the negative x squared plus y squared, and that was in terms of x and y, now becomes an iterated integral in terms of polar variables. And I can read off the bounds from this expression I've got here. Okay? So let's see, we've worked out x squared plus y squared is just r squared in terms of the polar variables. So that's going to be e to the negative r squared, and the dx dy we replace with the Jacobian by the d theta dr. And now the d theta in the iterated integral is evaluated from 0 to 2 pi, and r evaluated from 0 to the radius of the circle, capital R. All right. So now it's just a matter of evaluating an iterated integral, which is something we know how to do. Okay, but now it's in terms of the new variables. Even though I've made this observation at the start, the integral of e to the negative x squared dx is not expressible in terms of elementary functions. But that doesn't ever become an issue here, right? Because we've got this extra factor of r here. Now, actually, at this stage, note the integrand is a product of a function of r with a function of theta. Theta doesn't appear explicitly, but we can just take that function to be 1, and the bounds are all constant. So actually, what I can do at this stage is expand this out as a product of two definite integrals of the individual variables, and that's using the result. I promised I'd use this result quite a bit at the time. What was it? Page 59. The result on page 59, I'm pretty sure. Okay, that's that special case where the integrand factorizes into a function, or into functions of the two individual variables. All right, so look, in this case, there's a bug crawling on a bit of paper. In this case, there's a simple variable transformation. If you set u equal to r squared, you can sort out that second integral. So this one just evaluates to 2 pi, and this should evaluate to a half times 1 minus e to the negative r squared. All right, we can have a bit of fun with this, actually. Why not? I mean, don't you always want to do this? Take the limit as r goes to infinity. What does that represent then? So, actually, I've got a diagram here, right? Volume below a surface and above a region in the xy plane. Here we've got a circle centered at the origin, volume below this surface and above that circle. Now if we take r going to infinity, we take that limit, then the double integral somehow represents the volume, or at least it limits to the volume, below the surface z equals e to the negative x squared plus y squared, and above the entire xy plane. Okay, that's where you say, wow, really? Exclamation mark. And then you think about it for a moment and you start to question, what is he talking about? Okay, so in that case, the double integral, we've worked out the value here in terms of r. But now if we're taking the limit as r goes to infinity of this function, that's actually going to be a finite value. And that's where you say, wow. Right? Exactly. So the volume below that surface, but over the entire xy plane, it's converging in the limit to a finite value. Isn't that interesting? But wait, there's more. I mean, that's just the start of it, right? That's just the tip of the iceberg. What if we look at the volume above the quadrant where x and y are both positive. All right, actually this surface, z equals e to the negative x squared plus y squared, has a kind of radial symmetry, right? So if I look at the volume above one quarter or one quadrant, it's going to be the same volume over all the other quadrants because there's a symmetry about the x-axis, about the y-axis, indeed radial symmetry, meaning symmetry about the origin. Sorry, I wrote quadratic, I meant quadrant. The volume above the xy greater than or equal to 0 quadrant must therefore be equal to pi on 4, because this is the volume over the entire xy plane, so we divide that into quarters, so it's just going to be pi on 4. And I'll just say, since z equals e to the negative x squared plus y squared is radially symmetric. So what I'm doing here is just thinking about this double integral and thinking about it, about what it means in terms of volume. But now I've decided, for some reason, to impose this obscure limit as r goes to infinity and just see what happens, see what I can conclude. All right, so now what we'll do, continuing on with this, all right, so what I'm hoping to do here is just expand your brains a little bit, expand your minds, open to new and wonderful things. Consider this iterated integral of that function we started with, dx dy, but now only taking values of x from 0 to some number a, and same with y. So in the xy plane, what we're doing is just considering the volume above this square in the xy plane. And that's gone out of focus. Okay, so now this is the iterated integral. So it's going to represent the volume above this square in the positive quadrant and below that surface. So actually, I can use that property on page 59 again and write that as integral of e to the negative x squared dx times integral of e to the negative y squared dy, right? Both evaluated from 0 to a. Now these are the same function, they're just expressed in terms of x and y. Doesn't matter what I call them. If I were able to evaluate this integral, its value or its number would be exactly the same as this integral, right? It doesn't matter if I'm using x or y or whatever. So that's using the result on page 59. And then this is just going to be equal to the integral from 0 to a of, doesn't matter what I call this, I can call it t if I want, integral of e to the negative t squared dt all squared. So it doesn't really matter what I call it, but it's just going to be that same number multiplied by itself, which is just that number squared. All right, so now if we let a go to infinity, this implies that that integral from 0 to infinity, e to the negative t squared dt, all squared. So letting a go to infinity means we're now considering the entire positive quadrant. Right? This iterated integral is representing the volume above that quadrant, but we've already worked this out to be pi on 4, right, using polar coordinates. So that means even though I can't integrate this or write down the antiderivative of e to the negative t squared in terms of elementary functions, I can still work out that in the limit as this upper bound goes to infinity, it converges to that value of root pi on 2. In fact, some of you may have come across this special function called the error function, which is often written as ERF or ERF. There's no air, fire or water, but just ERF of x, defined in this way, 2 on root pi from integral from 0 to x of e to the negative t squared dt. And this factor of 2 on root pi that appears in the error function comes from this limit that we've just worked out. Right? The error function actually has a graph in the xy plane. looks something like this. It's a very rough diagram, but looks something like that, bound between 1 and -1. Okay, so I just wanted to show you the sorts of things we can do here. For example, even though we can't integrate, we can't write down the antiderivative of this function, we can still work out a value at that limit as the upper bound goes to infinity. So there's just something nice to consider. All right, this next example, look, I'll just... there's not really anything new in this example. It's just a good, solid application of polar variables. Typical sort of exam question, you know, find the volume of the solid bounded by the plane z equals 0. Remember, that's the xy plane. And the paraboloid z equals 1 minus x squared minus y squared. We can observe that the surface z equals 1 minus x squared minus y squared intersects the xy plane, and that is the plane z equals 0, when x squared plus y squared equals 1. Okay, so x squared plus y squared equals 1 in the xy plane, that's just a circle of radius 1 centered at the origin, right? So the volume of the solid bounded by by this region in the xy plane and that surface, z equals 1 minus x squared minus y squared. Perfect. I'll call that d. It's perfect for a double integral over d, and integrate that function 1 minus x squared minus y squared. Okay, that's in terms of rectangular coordinates, but because the region of integration is a circle, I think, well, that's where I'd better use polar coordinates. I don't have to, but it's going to make life a lot easier if I do. And so in terms of polar coordinates, I can easily write down an expression for this region, since it's bounded by a circle of radius 1, and it's the entire circle I'm interested in. Those bounds are easy to work out for polar variables. Okay, so then the volume is just going to be this iterated integral of, 1 minus x squared minus y squared. That's going to be the same as 1 minus r squared, right? We've already worked that out in the previous example, that x squared plus y squared was r squared. The Jacobian, and theta's integrated from 0 to 2 pi, r from 0 to 1. So that's a really straightforward integral. Again, I could just write this as a product of an integral with respect to theta and an integral with respect to r. So that's just, I mean, I can work it out straight away, right? 2 pi times a half minus a quarter, so that's just pi on 2. All right, so just a nice little example that's an application of polar variables. Right? But it requires a little bit of thought to set it up, and in particular to be able to identify that region as being a circular region. Okay, now this next example, there is something in this. This is an example that's worked in Stewart, and to be honest, I don't like the way they do it in the book. And I want to show you another way of thinking about it, but perhaps I'd suggest having a look at the way they work through it in the textbook, page 1025, example 4. They've got a fully worked solution of this done one way. All right, so the question is, find the volume of the solid that lies under the paraboloid, z equals x squared plus y squared, and inside the cylinder with this equation. And we can interpret that as saying that is above the circle in the xy plane, because they specify it's for only for z greater than or equal to 0. But anyway, above the circle in the xy plane, okay, how is that a circle? So we've got the equation x squared plus y squared equals 2x. This is one of those examples where we need to complete the square, right? So x squared minus 2x plus something, I'll leave that blank for the moment, plus y squared equals 0. Now in this case, if I add 1 to both sides, I think it's that easy. If I add 1 to both sides, I complete the square, because then that guy just becomes x minus 1 all squared plus y squared equals 1. So now we can easily identify that as a circle in the xy plane, but centered at x equals 1, y equals 0. And of radius 1. Okay, so here's the observation. And this is how the example is worked through in Stewart, right? Okay, so you look at this and you see it's a circle, all right? I should use polar coordinates, right? And so here's where I'll just point out that, yes, we could use x equals r cos theta, y equals r sine theta, but is it really going to be that simple? Okay, so firstly we've got a region in this half of the plane. So remember I was talking about circular regions or regions defined only for positive values of x. We could take as the bounds for theta negative pi on 2 and pi on 2. That was one of the things I mentioned, I think, on the very first slide I had up. But what would we use as the bounds? Remember, this r here is measured from the origin. So that means for the bounds, depending on the value of theta, the upper bound for r is going to change. All right, so the upper bound for r is going to depend on theta. Okay, so does this defeat the purpose of introducing a new set of variables in the first place? Okay, because now the bounds of the iterated integral, if we were to use these variables, the bounds are going to involve some functions now. They're not all going to be constant. All right, sometimes it might be useful, and I mean, to be honest, in this example, it's not so bad. Have a look at Stewart, page 1025, and see how that's worked through. Instead, one thing we could do is use, well, what I call shifted polar coordinates. Right? Now, because the circle we're interested in is centered at x equals 1, y equals 0, why don't we just redefine how we define r and theta? Okay, so in other words, given this equation of the circle, why don't we just set x minus 1 equal to r cos theta and y equal to r sine theta? It's going to amount to a much nicer description of that region. And then in this case, r is going to be the distance a point lies from the centre of the circle. Okay, and so in other words, x is just 1 plus r cos theta. Remember how I defined the Jacobian in terms of those partial derivatives? Right? Remember how I defined the Jacobian? If we worked out the partial derivatives, this 1 will always vanish. So actually, it's going to be the same Jacobian as before. So it's still going to be r. Now the only thing is that this function, so the surface z equals x squared plus y squared, that function, so x squared now is going to be this expression all squared, right? So that's going to be an r squared cos squared theta plus 2r cos theta plus 1, and then plus y squared, which is r squared sine squared theta. Okay, so we've got a trig identity we can use. So that'll give us r squared plus 2r cos theta plus 1. I'll just go over the page. Put this on the other screen. So that's the function we're going to be integrating, r squared plus 2r cos theta plus 1. And the region, so let's call this region D as usual. And then D will have just a nice, simple expression as all points, what is it? A circle of radius 1, isn't it? So all points with polar coordinates r and theta, with r between 0 and 1, theta between 0 and 2 pi, and then the volume in question is just the double integral of x squared plus y squared, which we can expand as an iterated integral using Fubini's theorem, but in terms of polar variables. So now that's going to be r squared plus 2r cos theta plus 1, same Jacobian, and theta is evaluated from 0 to 2 pi, and r is evaluated from 0 to 1. Okay, so, well now, I mean, it's just an iterated integral, right? You just integrate each term separately, and I mean, there's nothing much to that, right? Remember, work from the inside out, and just check the answer is 3 pi on 2, which actually agrees with Stewart, the calculation done in Stewart, as expected. The only thing to observe, though, is if we did use x equals r cos theta, y equals r sine theta, our surface would be a lot easier. It would just be z equals r squared, whereas we've got a slightly more complicated surface. So there's a trade-off here. But I maintain one of the reasons for using a new coordinate system is to make the bounds simpler, is to introduce it so that it's much more naturally associated with the region. Anyway, there's just some food for thought. Okay, guys, see you next time.